Hey, welcome to another fabulous day in Calculus 3. We're going to be looking at vector fields today. Exciting topic. Here's a picture of a vector field right here. Oh, but that just looks like a bunch of arrows. I know. A vector field is a graph of a collection of arrows. See that? When you look at a vector field, depending on the vector field, sometimes you can get a feel for the vector field. So this vector field right here, it looks like a swirling eddies of a jacuzzi or something like that. That's what it kind of reminds me of there. So it's kind of pretty. But that's a 2D vector field, and we're going to also be looking at three-dimensional vector fields as well. So good times, good times. Okay. So before we get into a vector field and the definition, let's do some review, because a vector field is actually a new kind of function. So let's go over the brand new functions that we've learned this semester so far that you're supposed to be aware of. So before I do this one here, let's just do the one that you did in algebra, basically, you know, your algebra functions of one variable. This is what you studied in algebra as well as calculus 1 and calculus 2. So it just looks like y equals f of x. And then does anybody remember what you feed it? I'll give you some choices. Do you feed it a point, a real number, or a vector? Anybody remember? Okay, you actually feed it a real number. Just a number like x. Give it the number x, and then the output, is that a point, a real number, or a vector? And that is going to be a real number. Now, well, where do points come into play? Well, if you were going to graph this function of one variable, you would take the collection of corresponding x and y points to graph it. But you actually don't feed it a point, nor does it poop out a point. This poop here is just a real number. Feed it a real number, poops out a real number. Okay, what's another function that we've studied this semester so far? Vector valued functions. We did that. Here's an example of what one would look like. R of t is equal to x of t, y of t, z of t. And I'm doing this review right now, and if I were you, I would like really be mindful of these, because your final is coming up in a month. And you got to know all of this and the distinctions between. So what did we feed a vector valued function? Do we feed him a point, a real number, or a vector?
A point?
Well,
Wait, no.
a real number. You fed it a real number t, like time equals 2 seconds, and then the output would be a vector, some constant vector a b, c for this 3D vector value function. So you feed it a real number and it poops out a vector. Okay, so far so good. What else did we say? So I should have done it over here because this is a vector value function. And now let's do another review. What we did here is we did functions of 2 variables. We did functions of 3 variables also. But let's look at a function of 2 variables, because we did a whole bunch of work on that in these past 2 chapters. So when you have a function of 2 variables, you know, it's going to, you know, this is not the vector field diagram. Sorry, I shouldn't do this one yet. That one's, I'm saving that one for the vector field. Let me do the function of 2 variables right here. So you've got some z equals f of x, y. So this is a function of 2 variables. Now, what did we feed a function of 2 variables? This is where we fed it a point. So we actually fed it a point x, y. And the output is a real number z. It's the altitude that is corresponding to the point that you feed this function of 2 variables here. Okay, so let's recap. You know about a function that has a real number input and a real number output, because you studied that in algebra, Calc 1 and Calc 2. We learned about vector valued functions here in this class, special kind of function where you feed it a real number, typically t, that's the parameter, and the output or the range is a collection of vectors. So another kind of function we learned, brand new function in this class, here we go, function of two variables. You feed it a point, x, y, that's an ordered pair, and the output is a real number, z. Now, if we had a function of three variables, you would feed it a point that would be an ordered triple, and it would still have an output of a real number corresponding to the ordered triple. Okay? Now, vector field is a new kind of function. So it's important that you kind of have an understanding of all the other functions that you studied so that you can make it the distinction between how it's alike and how it's not alike. Okay, so here in a vector field, see how this is bold right here, bold face? That means it's a vector. So when you have to put that on your quiz or your exam, you're denoting a vector field, you have to use this vector notation. And some of you know that you've experienced it firsthand, that if you neglect to put your vector notation on your handwritten work, I do take a point or two off here or there, just to remind you it's important. So when you have a vector field, it's different from a vector valued function. Oh yeah. So I'll do a two-dimensional one. I'll use my angular brackets because I'm going to write it in component form. And the first component is a function of two variables for this vector field of two variables, m of xy. And the other component is also a function of two variables. We'll call it n of xy. I do want to say that your textbook, which I'm not a huge fan of, unfortunately typically uses P and Q, which is not good. I'm never going to use P and Q in my lectures because traditional mathematics use M and N. And for those of you that are going to take differential equations next semester, or maybe the semester after that, you will thank me because you will study a differential equation that actually involves you finding, it's called an exact equation, and you're given an equation in differential form and you're asked to find the solution. And the solution is basically going to be a level curve in a scalar field for a vector field. And they use M and N in every single differential equation book that I've known. And if you can see my bookcase over here, I've got an entire shelf denoted here just for differential equations books, because I'm a big fan of differential equations, because I'm a former electrical engineer, and differential equations are God's gift to electrical engineers. Yeah. Okay, so M and N, so what do you feed it? And what is the output for a vector field? Well, you feed it a point. So now it's kind of looking like a function of two variables because you fed a function of two variables a point also. But the output is a vector. So that's the big difference. So you feed it a point, the output's a vector. Okay, so here's the official definition right here. This one is the 2D version, and then the second half is the 3D version. So the 2D version, a vector field over a plane region R is a function f that assigns a vector to every point in R, just like I have for my function machine diagram here. It assigns a vector to every point that it's given. And a vector field over a solid, which I like to call Q in space, is a function f that assigns a vector to each point in Q. So that's going to be an order triple. So furthering the definition, I just want to say that, you've got your two-dimensional, this is more notation here, fxy. I prefer component form when I denote a vector field, but I just want you to know that it's just as legit to use the I hat and the J hat here like that. Use my little I hat. And for a vector field of 3 variables, you're going to have 3 components here. Oh yeah. And the 3 components are going to be M, N, and P. Briggs uses P, Q, and R, whatever. And so you're going to have, if you want to use the I hat, J hat, K hat notation, that's legit. Totally okay. I'm personally not opposed to it. It's just that I don't prefer it. Okay, so that's just some more notation. Now what? Let's look at a question here. And this is review. Let's see how well we remember stuff from our last midterm. It seems like forever ago, doesn't it? What does the gradient for a function fxy look like? Well, we go del fxy, and if you recall, it was a vector that contained the first partial derivatives for the function. But look at how this looks here. Compare it to this. Don't they look real similar? Why is that? Because gradients are vector fields. Oh yeah. Write this down. That could be a true false question. You know what I'm saying? Gradients are vector fields. Now, is the reverse true? Are vector fields all gradients? Oh no. The reverse is not necessarily true. Be careful on that one. I could put that one as a true false also. True or false? Are all vector fields gradients? False. You'll see that as the week progresses. By Friday, this will become crystal clear. So just hang on while we, introduce some of the things we need to do here. We're laying down the foundation for the rest of this chapter. This chapter is an exciting chapter because we're going to be doing the vector calculus portion of the course. And it requires knowledge of all the previous modules. You have to know about vectors. You have to know about vector valued functions. You have to know about functions of more than one variable. You have to know about partial derivatives and all that stuff. Chain rule. Yeah, all that stuff. And gradients. And then multiple integration. Yep, got to know about that module also. Double and triple integrals. All that stuff is going to come into this module. You're going to feel like an Olympic athlete going for the Olympic gold in this chapter because you are. It's the culmination of everything we've learned. Good times. Here's some common physical examples of vector fields. These may look somewhat familiar. So velocity fields are vector fields that are describing motions of systems of particles like wind or water. So if you look at this velocity field, this is a rotating wheel vector field. Notice that the length of the vectors changes as you get further and further away from the axle of the wheel. The vectors get larger and larger. And why is that? Well, because the angular velocity is increasing. So if you were a bug and you had to decide where on the wheel that you would stay, I would, if I were a bug, so I'd be safe, I'd choose the middle of the wheel because essentially you're not moving. The further out you get when you're on the boundary of the wheel, boy, you're gonna fly off, Okay. So the greater the magnitude of the vector, the greater the velocity. Okay, we can also look at some more velocity fields like airflow over a car. That's fine. Let's look at another kind of vector field that our physics brethren like to cover a lot. Gravitational fields, defined by Newton's law of gravitation. So the force of attraction exerted on a particle of mass m1 located at a point xyz by a particle of mass m2 located at the origin is given by this vector field. Notice that the denominator, x squared plus y squared plus z squared, is actually the distance between the 2 points squared. So it's a distance squared. And notice that there's an inverse relationship there. So the bigger the distance, the smaller the vector will be. And so here's a picture of a gravitational vector field. So if mass M1 is, somewhere over here at point XYZ, and the other mass is sitting here at the origin, you'll notice that the vectors that are closer to the origin are larger, because the closer and closer that two objects get to each other, the increase of the force between them. Okay, and this is known as a central force field for obvious reasons. There's another kind of central force field known as an electric force field. And if you're in physics 2, you're probably covering that. A lot of electromagnetism in the second semester of physics. And yeah, a lot of what we're going to cover in this chapter is going to be helpful for second semester physics folks. Okay? So we talk about Coulomb's law, which states the force exerted on a particle of electric charge Q1 located at a point, and another electric charge Q2 located at the origin is given by this. And this almost looks like the other vector field. Yeah. You've got some constants and so on. This R squared is, again, a distance squared. Okay. So how do you sketch a vector field? So I'm going to go into massive detail on how to do this, more so than any other book I've seen, just because I really want you to get on how it's accomplished. You are going to have to pick pictures in your homeworks for correct vector fields. So if you know how to sketch them, you'll have a better shot at picking the right ones, not just like eeny, meeny, miny, mo, and guessing. Okay. So vector fields are just a collection of an infinity vectors. Well, does that mean every time I graph a vector field, I have to draw infinity vectors? Well, that would be silly. We can't draw infinity vectors. That would take too long, of course. Well, how can I get by and sketch the least number of vectors possible, but still maintain the flavor of the vector field? And the answer to that is you sketch enough representative vectors to help you visualize the field. And the way you do it is you use level curves in scalar fields. Well, what the heck is that? I'm going to get into it. So as I do this next example, you'll see exactly how I roll. So here is a vector field. Fxy is equal to a vector with components negative y and positive x. What the heck is that going to look like? Don't know. We're going to find out. So the first thing you're going to do, because you don't want to draw, 50,000 vectors, is you figure out the level curves in scalar fields. So step 1 is you're going to set the magnitude of the vector field equal to a constant. So this probably looks very familiar to you, because it's similar to finding level curves for a function of 2 variables. You set the function equal to a constant. But here it's almost the same. You set the magnitude of the vector field function equal to a constant. So the magnitude for this function is the square root of y squared plus x squared. But if you square both sides and rearrange things, this looks like circles. And that's what the level curves look like for this vector field. So what does that mean, level curves? Well, it means that any point on one of these circles, and if as long as you stay on that same circle, those vectors will share something in common, the same magnitudes. What the heck are you talking about? Let's let C equal 1. And if you draw a circle centered at the origin with C equals 1, that's going to be a circle with radius 1. And let's pick 4 points, 4 easy points off of our circle of radius 1, and then make a chart. Yeah, this is going to take some time. Did you think it was going to be quick? Ah, sorry. So, I'm going to pick the point 1, 0, 0, 1, negative 1, 0, and 0, negative 1. And I'm going to put those in my chart. Now what? Hang with me here. Now, what vector gets associated with each point. Now keep in mind, this vector field has a vector negative y, x. So if I put a vector here with angular brackets, negative y, well, negative 0 is just 0, and then x. So the vector 0, 1 is associated with the point 1, 0. How do I sketch that? What I do is I first sketch the vector 0, 1 in standard position, and that's easy because you just find the point 0, 1 and then draw a vector in standard position. Remember the initial points at the origin. And don't leave it there. You need to translate it so that you maintain its orientation and magnitude, and then draw it where it's coming out of, or its initial point is coming out of the point that it's associated with. So we just did that one. And now let's do the next point. The point with coordinates 0, 1, that's this guy up here. What's the corresponding vector for that guy? Well, negative y, so he has a y coordinate of 1, so negative 1, comma, the x coordinate is the y component, negative 1, 0. Well, what if I drew that guy in standard position? Well, negative 1, 0, you first locate the point negative 1, 0, and then you draw a vector with the terminal point at that negative 1, 0, and then don't leave it there. Bring it over where it's associated with the point 0, 1. So we're making progress here. And then next up, the point negative 1, 0, his vector will look like 0, negative 1. If you graph 0, negative 1 in standard position, that's a downward facing arrow of magnitude 1. And then finally, the point 0, negative 1, negative y is negative, negative 1, which is positive 1. And then x is the other component. 1, 0 is a vector pointing to the right of magnitude 1. And so you bring that over and have its initial point there. Now, is that enough? Is that going to be enough vectors? No, it's not. I would not give you full credit if this were your drawing. I do want to say that if you did pick any other points along this circle, and you can kind of eyeball this, that they would all have magnitudes of 1, because it looks like everybody who's on this level curve has a magnitude of 1. And it would also have the sort of same relationship to the circle. It looks like all of these vectors are tangent to the circle. Is that always the case? Oh, no. But it is for this vector field. Okay, so I would have you, you wouldn't get full credit. You'd have to draw one more level curve for me. Okay, fine. Well, what if we let c equal 2? So then our circle is x squared plus y squared equals 4. So here's our new level curve. And let's pick 4 points off of this curve. And those 4 points we will put in our chart. And then we're going to, I'm going to do this a lot faster now. And then you're going to figure out the vectors that go with these points on this larger level curve. So the point 0, 2 will have, we want negative yx here, so we'll have 0, 2. If you draw that in standard position, that's a pointing upward vector, and then you'd want to bring it over here to the point it's associated with. There it is. And then 0, 2 is going to have negative 2, 0, and that's a vector pointing to the left of magnitude 2, corresponding to the point 0, 2. And then this third point, negative 2, 0, would have the vector 0, negative 2, and that's a downward facing arrow, vertically downward. And then finally, 0, negative 2 would have 2, 0. That's pointing to the right. So it looks like the further away you get from the origin, the vectors get larger and larger. That's sort of the flavor of this vector field. Now, to prove it, I could easily go into my my graphing software, which you've seen before. Oh, what happened to them? Okay. Getting bigger here. So this graphing software, what I like about it is it allows you to do vector fields, which are kind of cool. And so the way you do it is you first grab a vector, in this case, a vector with components x, y, and then you set it equal to another vector. And then in the second vector, you put what the actual components are. So the real component, for us is negative y. And then the y component for us is x. And then I think that's good enough. And then I'm going to hit it. Let me just make this a little larger here. Woo. Okay, so you can see that this vector field does look like, kind of looks like a jacuzzi. And the little arrowheads are little dots. You can see that it's whooshing around. Looks like it's whooshing counterclockwise. Pretty cool, huh? I can change the color if you don't like that. How about blue? Oh, pretty. I don't have that many choices though, unfortunately. How about red? Oh, yeah, okay, pretty. Yeah, that's a nice looking vector field, isn't it? I know. Okay. So that's that vector field. Okay, fine. Let's move on to the other vector field. Hope you're having a good time. This isn't very hard. If you're thinking, wow, this is easy, I got it. Good. We want our introduction to be nice and easy, because things can get a little tricky as this chapter progresses. So we want to start out gently. It's a nice, gentle intro for you. Okay, how about this new vector field, 2xy? Well, is it going to have circles as level curves? No, 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 no.
Do we start with the magnitude?
Yeah, you got to set the magnitude equal to a constant. So, that's going to be different for this particular vector field. So then you get that. But this is ellipses, folks. So we're going to have ellipses, and not just any ellipse. Don't just start drawing ellipses here. Oh, yeah. No. They have to fulfill this equation here. So you have to be careful. You don't just draw any old ellipse and get sloppy. Yeah, your calculator, your calculator, unfortunately does not have the ability to graph vector fields. And that's why I'm going over in massive detail how to do this by hand. Okay. So what about these ellipses? How about if we let C equal 1? So what of it? So you do have an ellipse that looks like this. Okay, now the standard look for an ellipse, and you probably saw this in a pre-calc class, looks like that. So the good news is I do have a 1 on the right-hand side, so check. But I don't want to have a coefficient here. I want something down in the denominator because that gives me information about the x and y intercepts. So would you guys believe that multiplying by 4 is the same as dividing by the reciprocal? Please say yes. So now plus or minus the square root of 1/4, which is plus or minus a half, is those are going to give me the x-intercepts for this ellipse. And then plus or minus the square root of 1, which is just plus or minus 1, will give me the y-intercepts for this ellipse. It's kind of a skinny ellipse there. And then you can go ahead and do your chart. And so for this, I'm going to just pick 4 easy points off of this ellipse. Of course, the ones that are on the axes, a little bit easier. And those are 1/2, 0, 0, 1, -1/2, 0, and 0, -1. And then honoring the vector field here, which is 2xy, twice a half is really 1, and then y is just 0. The 0.01 will give me twice 0, which is 0, 1. And then a -1/2, 0 will give me a -1, 0. And then the last point, 0, -1 will give me 0, -1. Now, when you graph these in standard position, like 1, 0 is pointing to the right with a magnitude of 1, 0, 1 is pointing up, -1, 0 is pointing to the left, 0, -1 is pointing down. But you have to draw them attached to the points that they're associated with. You can't just leave them there in standard position. So this first point here had 1, 0. So you draw a magnitude of 1 vector, 1, 0, pointing out. And then this guy here had the vector 0, 1, so he's going to look like that. And then this point over here, negative 1, 0, so his vector is pointing to the left, magnitude 1. This point here, 0, negative 1, so it's pointing down with a magnitude of 1. So all the vectors that live on that ellipse are pointing outward and have magnitude of 1. So I could just sort of, this is kind of cheesy, but I could put some other points on that ellipse would have vectors as long as they're pointing out and they have a magnitude of 1, I can kind of fill it in. Are those enough vectors to get the flavor of this vector field? No, not enough. Well, how many do you want? 1 million? No. I want to know the flavor. Like if I get further away from the origin, will my vectors get smaller or larger in magnitude? That's a good question. So let's do at least one more ellipse for this particular graph. So that way we'll get the flavor of it. So in my level curve in scalar fields, how about we let C be some other number? How about C equals 2? Okay, so what of it? So let's let C equal 2 instead. So then we'll have 4x squared plus y squared equals 2 squared. So then what will this ellipse look like? And you got to honor it. Don't just draw any ellipse. It's got to be one of these actual ellipses from your scalar fields. Now, we like this to be a 1 when we're comparing this to the standard format for an ellipse centered at the origin. So how about if I divide both sides of the equation by 4, and then that will get me a 1 over there. Oh, cool. Now it's in standard form, and now this is an ellipse whose x-intercepts are plus or minus square root of 1, which is 1, and whose y-intercepts are plus or minus square root of 2, or square root of 4 rather, which is plus or minus 2. So oops, I gotta do this right. Because the y is plus or minus 2, the x is plus or minus 1. I gotta make sure I draw this ellipse right. So it's gonna be this kind of skinny ellipse like so. And then we'll just pick the 4 points off of that ellipse that are on the axes. That way it's easier. And then I can continue my chart here. If I'm continuing my chart, I got some more points here. I got 1, 0, 0, 2, negative 1, 0, and 0, negative 2. And this is when C is equal to 2. And then I fill in the rest of my chart here. The vectors that go with those points are going to be, this one's going to be 2x, that's 2, y, that's 2, 0. This guy will have 0, 2. This guy will have negative 2, 0, and this guy will have 0, negative 2. And then when I draw those 4 vectors, I can first draw them in standard position and then swing them up here. Those vectors are also going to be pointing outward, and they're larger magnitudes. All of these guys have a magnitude of 2, so they're larger. Gonna make them longer here, but they're still all pointing out. And you can kind of sneak in some more as long as you're on that level curve. They point out with a magnitude of 2, and I think that's good enough. We've given a good look of what this vector field is looking like. And of course, I could actually go to my graph, my graphing software, which is pretty cool, and I could graph that vector field. So this one where the x component is twice x and the y component is simply y. And let's see what this guy, let's see if we got it right. Woo! Does look like they're all pointing out. And so that looks like we've got the nature of the vector field. Yeah? All pointing out there. Whoosh! And the vectors get larger in magnitude as you head away from the origin. So that's kind of nice. Just a little peek into that. And then the last one I have, I'm not even going to bother doing the scalar fields for an obvious reason, because it's a constant vector field, a letter C here. So you don't have to do any figuring out. Since this one is not having any variables in it, don't bother going through that whole magnitude thing. You're going to waste time. So don't do this. Not necessary, because this is a constant vector, it means every single point in the two-dimensional plane are going to have vectors that look like 0, -1/2. And those are vectors that are vertically downward. So if you could pick, you can pick a few points anywhere here. I'm just doing crazy here. And they're all going to be pointed down with a half, a vector, a magnitude of a half. They're very kind of small vectors all pointed downward. Yeah, a whole bunch of them. Just draw them anywhere. Any random spot will do. And so you get the drift. That it kind of looks like rain, doesn't it? Yeah. We got rain. It's raining. It's raining small vectors. So all the points have the constant vector associated with it. So that one's easy to sketch. Now, last, the 3D vector field, and these are hard, and I'm not going to go over how I would graph that. I'm not going to make you figure it out either. But I do want to say that this one's interesting. It's not as hard as some would be, because the first two components are zeros. So only the z component does something. And so all the vectors point in the z direction. Okay. So if you were just going to look at a small region in 3D, if you were going to look at here in the XY plane, a circle of radius 4, and you were just going to look at all the points that live in this circle here in the XY plane, this is kind of cool because this vector field looks really sweet. The vector that is centered, corresponding to the origin here, is the longest. Going to be square root of 16, which is 4. And then the vectors, as you get further away from the origin, they're going to point up, but they're going to be less. And then if you get further away, they're tinier until you're basically down to nothing. So it's kind of looks like when you're squeezing a tube of toothpaste, this is like the velocity field of your toothpaste. Bet you never thought about that when you were brushing your teeth, huh? Yeah, the toothpaste in the middle is going at the fastest velocity, and the toothpaste, as it gets closer and closer to the edges, that toothpaste isn't going nearly as fast as the toothpaste in the middle. Okay. And then when your mom asks you, hey, what'd you talk about in calculus today? You could go, we talked about the velocity of toothpaste. Oh, I cracked myself up. Okay, so this 2D vector field, I didn't show how to graph in slow motion, but the vector field is given up here. If you were to, because my graphing software kind of is different, you would probably see it written as f xy equals, and then you'd see an angular bracket here, cosine y, comma, sine x. And so this is the picture of that vector field. That's a nice looking one. I think it's kind of pretty here. And I have another one for you. Let's see if I can pull it up for you. So this one, this 2D vector field is kind of odd. It's not your usual. Place the cursor in the equation below and adjust the resolution slider. Oh, let's see if this, we do this. So here's a 2D vector field. Interesting. And it's got some animation built into it. No, it doesn't. It doesn't work. 0.22. Now I can't make it move. Ah, too bad. All right, so this vector field's a little bit odd. It's kind of hard to tell, what the pattern is. It's different. Very different. So the point I guess I'm trying to make is all vector fields are going to have a different look, right? They're not going to all be the same. All right. Let's talk about conservative vector fields. Okay. So in example B that we did, I want you to notice that all of the vectors in example B, that's where all the vectors were pointed out right here. Ooh, that was not nice. Sorry. All the vectors in letter B here are pointed out. And in fact, all of those vectors are normal to each of the level curves from which they emanate. So fill in the blank there on your course reader lecture notes and put in normal And we mean, when we're talking about normal there, we're talking about orthogonal essentially. And because this was a property of gradients, I hope you remember that from our last module, that gradients, when you sketch them, they're always orthogonal to level curves. The question could be, could this vector field given by fxy equals 2xy be a gradient for some differentiable function fxy? And the answer is yes. And that is a big deal for us as well as for physics folks. So here's the fact. Some vector fields can be represented by gradients of differentiable functions, but not all, and this is key, not all, And the types that can are called conservative vector fields. Now let's do the official definition of a conservative vector field. Here you go. This is very important. Could be a true false question, right? Or maybe change up the definition to see if you got the definition. A vector field, big F, is called conservative when there exists a differentiable function, little f, such that big F is the gradient of little f. And this little function f is known as a potential function for f. If you're still confused, don't worry, because hopefully in the next part of this lecture, we'll have the fog lift a little bit. Really, really important. Now, the word conservative isn't the kind of word conservative that you may associate it with. It comes from classic physical law regarding conservation of energy, where the sum of kinetic energy, the energy due to motion, plus potential energy, the energy due to a position in a force field, is equal to a constant. That is, kinetic energy plus potential energy is always constant. Thermodynamics. I have a meme for you at the end of this section that has to do with that. It's kind of fun. Physics. So how do you tell if a vector field is conservative or not? Are we going to have to sit here and sketch vectors and make charts, which takes forever and is kind of annoying until we figure out, oh, well, this is a conservative vector field because, hey, look, all of his vectors are orthogonal to the level curve. So this is a conservative vector field, whereas letter A is not a conservative vector field. Not. Well, why not? Well, because the arrows are definitely not orthogonal to the level curves. In fact, they're tangent. So this guy is definitely not a conservative vector field. So you can tell by looking at a picture, but that just takes too darn long. Is there a quicker way? Man, there is. Thank you, God. There's a way that's faster. And you're going to use this theorem. This theorem is the easy way to tell. And this is for 2D. I won't show you the 3D test until another week or so, but it's somewhat similar. So that's good news. So let's say that you have m and n, which are functions of two variables, and they have continuous first partials on some open disk region R. Then this vector field F with the components m and n is a conservative vector field if and only if, when you take the partial of n with respect to x, it is exactly the same as the partial of m with respect to y. If those are equivalent, boom, you have a conservative vector field going on. You don't even have to draw a picture. Okay, so this is your test for conservative vector fields. So the thing about this test, though, is after you go, yes, my vector field's conservative, woohoo, what does that mean? It means that he's somebody's gradient. But what if somebody said, well, who's gradient? Give me the function he is the gradient of. And that's known as the potential function. So how do you find that potential function for your conservative vector field? Because that means he's a gradient. So, once you have a gradient, wouldn't it be nice to know who you're the gradient for? So I'm going to give you the Rasky way to get the potential function. If you find the potential function in any other way on your quiz or exam, I will not give you credit. Telling you right now, no credit. You will do it my way or the highway. Well, gosh, that's very narrow-minded of you. No, it isn't. I'm actually giving you the easier way, because the other way that you'll see in books is somewhat of a nightmare and kind of confusing. And my way works every time. And if you're going to follow it, you will be happy that you did. So consider it my gift to you. Did I make it up? No, I didn't make it up. Some other professor that I had way back in the day, in my electrical engineering undergraduate days, shared this gift, and I want to share it with you because it's great. It's going to be the way to go. But you have to watch closely because there's some rules and regs about how to do it. Okay. So here's some examples of what you'll see on a quiz or an exam in the future. Not your midterm though. Okay. Your midterm's not going to, midterm 3 is not going to have this on there. Midterm 4 will though. Haha. Okay. So this is a two-part kind of thing, because you first have to answer the question, is the vector field conservative or not? And if yes, that means he's got a potential function to go get. If no, you're done. A vector field that isn't a conservative vector field doesn't have a potential function associated with it. Okay, because he's nobody's gradient. So I like to think of this as, if you have a conservative vector field, he has a mom, and you got to go get mama. Go get mama. Okay, so we're gonna see when we have to go get mama. Okay, here we go. Letter A, fxy. That's a nice vector field. Okay, the components are x squared y and xy. Okay. Is that conservative or not? Well, don't guess. Don't go, well, that looks like it should be. No. That's not going to work. You can't guess. I can't even guess. The first component is M for Mary, and the second component is your N for Nancy. And you have to check, is dn dx the same as dm dy? So let's do this. What is dn dx equal to? Well, when you take the partial derivative of xy with respect to x, I get y. Okay. What is dm dy equal to? So what is the partial derivative of x squared y with respect to y? I think it's x squared. Well, folks, these are definitely not equal. So no, it's not a conservative vector field. It's still a legitimate vector field though, okay, people? It's just not a conservative vector field. You know, it's still, you could still graph it and, you know, do stuff with it. You know, it's just not going to be a conservative vector field. Man, this computer's driving me nuts. So, I mean, I could even graph it if I like, well, what does it look like? I don't know. What does it look like? I have no clue. You could, you know, go and graph it. I think GeoGebra, for those of you who are in it, you know, you want to know what, I want to graph some of these on my own. Sure you do. GeoGebra does have a way to graph vector fields. You may have to read or watch a YouTube video on how to do it, because it's not super easy, but certainly it is doable. Now, this vector field does not look that exciting. Oh man, this looks like a bunch of dots. Let's see if I zoom out a little bit. That's not helpful. So I'm kind of getting far away from the origin. It looks like you don't have much. Interesting. Yeah, this is not a very fun looking vector field. Okay, fine. Moving on. Okay, how about the letter B? Is that guy conservative? Because if he is, then we can go get mama. All righty. Now remember, this is the same vector field that I just graphed. Same as our graph. So we already know the answer. He is a conservative vector field, but let's just show it analytically though. So remember, the first component is understood to be M and the second component is understood to be N. Please don't make these look backwards. So let's get dm dy. The partial derivative of 2x with respect to y is 0. Fine. Let's get dn dx. Well, the partial derivative of y with respect to x is 0. Are these the same? Yep, they are. So yes, It is a conservative vector field. Now, what does that mean? Go get mama. Who's mama? That's the scalar function, little f, who, if you did take the gradient, this would be the gradient. This would be del little f. They're one and the same. So we got to go get little f. Now, watch closely how I do this, because this is not how the book does it. And, you know, for those of you who go like to chase things down online and copy and paste, be careful. I'm not going to accept your work from that, or any of those apps or websites. Got to do it my way. My way or the highway. Here we go. It's not that hard. You're going to do a couple of integrations. You're going to integrate m with respect to x. And then you're going to integrate n with respect to y. And you're going to add the results together, but with one huge caveat. So when we get to the caveat, I'll let you know. This problem doesn't have the caveat, so we'll see. So this one, you're going to integrate the first component, 2x, with respect to x. Oh man, that's easy. That's just x squared. Now, I'm going to dock you a point every time you forget to put something. You're not going to put plus c. You're going to put plus something that could be a constant, but it's actually, since we are only recovering mama with respect to x and there's still more, you're going to say, okay, it's going to be like a function like h of y, which could be just a constant, but you need to put that if you're going to be allowed to use my way. That's the one little payment you have to make. And I know who's watching my videos and who's not. Okay, so we're going to integrate n, which the n for this guy is y, dy, and that's easy because, shoot, that's just y squared over 2. But plus extra junk. So what's the extra junk? It's some function, we'll call it some other letter. You have to use different letters, like don't use h again because you already used h. I'll dock you a point. G, and since we're integrating with respect to y, it'll be the other guy, g of x. Now what you're going to do is you're going to look at what we have here, and your mama function, fxy, is going to be the sum of those two plus a constant. Okay, and we're done with letter B. This is what's known as the potential function for our vector field. This is what I call mama, okay? So I'm going to do one more, and then you're going to try one soon. You're going to do letter D, so watch out. So letter C, is this conservative or not? I don't know. Let's do the test. Oops, the dm dy, the derivative of 2xy with respect to y is 2x, okay? dn dx, the derivative of x squared minus y with respect to x is 2x. Hey, these are the same. Good news. Yes, it's a conservative vector field. Go get mama. Go get mama. Now this one's going to be harder than the last one. This is where I'm going to show you that caveat for this type of strategy that I'm showing you. So you're first going to take the integral of m with respect to x. So what is the integral of 2xy with respect to x? You know, be careful. You're integrating with respect to x. So that would be x squared y plus extra junk. So what are you going to put? H of y for your extra junk. Okay, so let's write that down. So you're going to go x squared y plus h of y. Okay, fine. Then you're going to integrate the n with respect to y. So you're going to integrate x squared minus y dy. That's a minus in there. Okay, not too hard. This looks like it's going to be x squared y minus y squared over 2 plus extra junk, g of x. Then what? I want you to notice something that just happened. And this is, and if you're not paying attention and you blow this, I don't give any credit. I'm like, you didn't listen. Too bad. You snooze, you lose. Do you see that we have duplicates? I want you to look here, duplicates. Oh, yes, I see. We do have duplicates. We got an x squared y in that integration result, and we have an x squared y in the other integration result. Should we add them together? No. Do not add them together. What do? You take one instance of them only. So your mama function, fxy, you'll have one of the x squared y terms. Don't add them together. I always know who listens to my lectures because the people that start adding these together and going, yeah, x squared y plus x squared y is 2x squared y. And I see that in their answer. Do not listen. And then we also have the minus y squared over 2, and then put plus a constant. And there you have mama for that particular example. Okay? So I'm going to tell you a quick story about mama, and then you'll try the next one. I had a student from a while back. He's now an engineer at Spayware. I think they renamed Spayware. I can never remember the new name. Anyway, he took me for like Calc 2, Calc 3 programming, and went to UC Berkeley and got his, I think he got his nuclear engineering degree there. Yeah. So he told me when he was at UC Berkeley, there was some upper engineering class where they were working with vector fields, and they had to go get mama. And, you know, that's not a technical term. And he was telling some of his classmates, oh yeah, I know how to do these problems. And they were like, they didn't have, you know, as good instruction. I don't know where they came from. They had no idea how to do the problems. And so he was tutoring them. And then he was going, yeah, go get mama. And they were like, okay, yeah. So he knew it well enough to tutor his classmates. So that's just a heartwarming and inspiring story that I love to share with you, because it's all going to pay off someday for you. Okay. So you're going to try the next problem, and we'll put you in breakout. Was this a conservative vector field? Yes or no?
Yes.
It was.
It was, correct. And so since it is conservative, you got to go get mama. Mama is the potential function when you take her gradient, you get back to the vector field. So let's see how this works, because this was a little bit tricky of a problem. It certainly was a little bit more involved than the ones that I did. And I did that on purpose because, you know, you guys are all good at integration now. Well, you're taking a test this Monday on it, so you should have some knowledge. So this first component is understood to be m, and the second component is n. So the question is dm dy equal to dn dx? Because if yes, it's a conservative vector field. And then you can go get mama. If not, don't go and do anything else. Stop. If it's not conservative, don't go get mama. There is no mama. You're done. Stop. I have some people go, no, it's not conservative. And then they go off and get a mama. And I'm like, what are you doing? You know, minus 50 points. No, you missed the boat. Okay. So my m, when I take the derivative with respect to y, the sine of 2x is just a constant. So the negative 2y cubed gives me the factor negative 6y squared. And then times sine of 2x. Now, what about n? Now, n, when you take the derivative with respect to x, and I like to distribute that 3y squared. The first term doesn't even have an x in it, so that's 0. The second term, when you take the derivative of cos 2x, you're going to get negative 2 sine of 2x, and that's multiplied by the 3y squared. So I'm just going to copy down the 3y squared. But then this is going to give you the same as dm dy. So these are the same. And so, yes, it's a conservative vector field. So you're like, okay, great. Let's go get mama. Let's go get that potential function then. Okay, here we go. So you're going to integrate m with respect to x. So you're going to go, what is the integral of negative 2y cubed sine 2x dx? Okay, the negative 2y cubed is just a constant multiple. So, you know, it's just going to go along for the ride. You're going to use u sub here with the sine rule, because sine u du is, you know, equal to minus cos of u. U is 2x. Du is 2 dx. I need a 2. But hey, there's one right there. So why don't we just use it up? Sure. So I'm just going to use that guy up since I already have a 2. And now this is looking like negative y cubed sine of u. Yeah. And then I'm going to go, all right. So then what was u? Let's put it back in. I think it was 2x. And then don't put plus c. You got to put plus something though. And put plus like h of y. And then save that for later. Then what? Well, then you're going to, oh, I forgot my negative. Sorry, this is, I forgot my negative. So this should be, what am I doing here? Oops, I'm totally blowing it here, people. Let me do my intermediate step. Trying to go too fast. Negative y cubed times negative cos u. Then we should get a positive y cubed. Sorry, trying to do this too fast. Y cubed cos 2x plus of h of y. Okay, so we'll save this for later. That's not the answer. Like, oh, I'll give you 1 point partial credit, 2 points partial credit, maybe if you got that far. It's like, yay. Then what? Now you're going to go n dy. Now this n up here is kind of a hot mess. So if you want, you can leave the 3y squared out. I'm going to distribute the 3y squared just to eliminate parentheses. You can do it how you want, just so long as you maintain everything mathematically, and I'm okay with it, okay? So this integral, you're going to integrate with respect to y. So be careful. So, okay, 3y squared, integrate with respect to y. Fine, I get y cubed. Plus 3y squared cosine 2x with respect to y. Well, I get y cubed times cos of 2x. Plus stuff. It's going to be extra junk that involves x since we didn't integrate with respect to x at this moment. So it could be just a constant, but you say it's a function g, something other than what you used up here. You use an h here, use a different letter. So now what? Well, you got to put it all together, but you have to be careful because I'm noticing here that I have duplicates. Should I add the duplicates together? Oh, no, you don't. Just take one. Just take one instance of the duplicate. Always just take one. Well, is there ever a time you're going to add them together? No, never. So your mama function, write fxy. Please write this. Otherwise, I won't give you full credit. You got to label who the function is. You got a y cubed plus one instance of the y cubed cos 2x. And now you can put plus c. And there is your potential function. Okay? So why does this theorem that involves the test for conservative vector fields work? Which basically says if dm dy is equal to dn dx, then that means you have a conservative vector field. And remember, a conservative vector field is one that's a gradient. It's a gradient. And that's kind of key that you get that. Because you guys know all about gradients, because that was in a previous module for the course. So we're going to complete a little mini proof that's going to prove why this test works. And it's kind of cool. What I love about this test and this little mini proof is it connects some of the stuff we learned about a month or so ago with what we're doing now. So it's kind of a lovely connection of some of the concepts. And I love that when we're making connections. Okay, so suppose you have a potential function, little f, that's a mama function, that when you take her gradient, you get a vector field, mn. Well, what do you know about gradients? We know that gradients, by definition, the components are first partials. So this is what we know, okay? So what we're saying is that the fx has to match whatever that m function is. And we're saying that the fy had better match what the n function is. Okay, that's what we're saying. Okay, they're equivalent. So what? That doesn't tell us anything. Well, hang on a minute, though. Hang on a minute. If you take fxy, which means take fx and take its partial with respect to y, that will give you m partial with respect to y. Okay? Yeah, so what? No, we're getting somewhere, trust me. And then when you take fyx, which is basically saying take fy, but then take his partial with respect to x, that would be the same as saying, let's take the partial of n with respect to x. Fine. But we know that when we were studying partials and second partials, that fxy and fyx are called mixed partials. They're kind of like the mixed up kids. And there was another theorem back when we were covering partial derivatives that says that mixed partials are equal. So if fxy has to be equal to fyx, we're saying that my has to be the same as nx. But that's basically saying the same thing as dm dy has to be the same as dm dx. Okay? And so that is the mini proof of why this all works out, in that conservative vector fields are gradients, and they are gradients from some potential function. I like to call it the mama function. Okay. And I think that concludes today's lecture. So congrats, and we'll pick this up and take a little further next time.